in gravitational field we discuss about the Newton's law, that is very much important and very simple, right? You find that many questions are related to this concept and this is very easy to solve. And then we drive Kepler's law, right, to link with the centripetal force and with the gravitational force, right? And then this is the last topic that we discuss about till see Kepler's law. Okay, and law is very much important because the derivations, you know, that they were included in our exams also. So that's why Kepler's law is very much important. Okay.
Yeah.
Okay, now the next concept is also related to the derivative part, because in this chapter we are having many concepts related to the derivative part. So the next concept is relative to gravitational field strength. Gravitational field strength means the value of a small g. Okay, so the next concept is related to driving gravitational field strength. Gravitational field strength, right? So basically we know that gravitational field is strength at a point that describe how strong or a weak gravitational field is at that point, right? Let's suppose if we are on earth surface, right? So we know that the gravitational force or the gravitational field strength is very much strong. Okay, just like if you place a metal piece near the magnet, so if metal piece is very close to the magnet, so magnet will quickly attract that metal piece, right? And if you place that same piece with increasing the distance, like at the twice distance, so magnet will attract that object very slowly, very with very weak force, right? So that is the same concept with the gravitational field, right? Once you are moving away from the earth, so gravitational pull will be less on your body, and once you get into the space, so there will be no gravitational pull of the earth on your body, because now you are out from the range of gravitational field strength, right? Clear?
Yes.
So basically, let's suppose if they ask you, because before derivation they usually ask the define gravitational field strength. I think we didn't discuss that thing, right? Gravitational field strength. Okay, yes, we discussed a small g, right? A region or space where a mass experience a force due to gravitational. So that is the concept of gravitational field strength. And we can say that, okay, so I'm writing in short the small value of g, and you need to write the gravitational field strength. Okay, so the gravitational field strength at a point describes how strong or weak a gravitational field at the point. So this is the definition for gravitational field strength. And let's suppose if we want to start with the derivative part. So for the derivative part, let's suppose if we are having Earth surface, right? So on the Earth surface, let's suppose if body is at some distance from the Earth surface, like at this point. So you know that Earth will try to attract this object towards the center, because gravitational field is always towards the center or always in downward direction, right? So one more thing that we studied, that gravitational force is always attractive. It will never be repulsive, right? Just like the electrostatic force and the magnetic forces, right? So that's why earth always try to attract the any other object. And for law of attraction, what what is the law that is related to force of attraction? That is Newton's law of attraction, right? That is between two bodies. So let's suppose if we start from the reference of Newton's law. So Newton's law of gravitation states that the force is directly proportional to the product of their masses and inversely to the square of the distance, right? So this is the concept of gravitational field strength, and this is the first equation we taken from Newton's law of gravitation. Now the second thing we know that we discussed in the concept of gravitation field. So in gravitation field, you have equation number one that shows you that a small g is equals to F over m. So the second equation we take the reference from this equation number one. So your final equation will be g is equals to F upon m. Okay.
Okay.
And now we know that we just simply replace the value. Okay. So basically in equation 2 we are having f, and that same f is also written in equation number 1. So we can easily plug the value of fg into the equation number 2. So your equation number 2 will be, if we just substitute the value, substitute the value of g, sorry, of f in equation number 2. So your equation 2 will be look like this. Let's suppose m will multiply on the left hand side, and on right hand side we are only having a value of f is gmm over r square, right? And now you can see that a small m can be cancelled out from each other. So we can easily cancel out this small m on the both sides, and finally you get the value of small g, and that small g is actually equals to capital G into mass of earth divided by radius, or the square of the radius. So this is an other important equation that we drive that is related to gravitational field strength, right?
Okay.
One equation that we drive that is known as the law of gravitation. Second concept we discuss is G is equals to F upon M. And this is the third gravitational field strength concept, which is equals to Gm over R square, right? And you know all the components in the concept, that what are these components and why we are using that concepts. So you know that capital G is the gravitational constant, right? And capital M is the mass of the earth, and small r square is the distance between the earth and the object. Okay. Just like the law of gravitation. Okay.
Okay.
And the next thing is one more thing, we are talking about gravitational field strength. So normally we just drive a formula. Let's suppose if they ask that gravitational field strength is a scalar quantity or a vector quantity. So it is a scalar quantity or a vector quantity. What do you think?
Scalar only
Yes, scalar
magnitude.
contains only magnitude. And if we talk about this gravitational field strength, so what do you think that this will be a scalar or a vector quantity?
Vector.
Vector, because we know that it will always attract you towards the center. So it there is always a specific direction during gravitational field strength, right? So we can say
Yes.
that the value of G, or we can say that the gravitational field strength is a vector quantity And the next thing is the direction is all towards the center. The direction is always towards the center. And the third point is, let's suppose just like the same thing we discussed, that on Earth's surface we are having constant value. If we are talking about only on the Earth's surface, so your value will be equals to 9.81 Newton per kg, right? And we know that outside the Earth's surface, the value will be not constant. So your value will be not constant outside the Earth's surface. So it will not remain constant. And if someone asks you that what will be the value of g if we are moving away from the Earth or if we are moving towards the Earth, so from the formula you can say that the value of capital G and M remains constant. Okay, so we are only having a value of g and r square. So we can just explain the fourth point like this: value of g with the value of 1 over r square, right? Because capital G, capital M both are constant. So basically your the value of G decreases as the value of R increases, because both are inversely proportional to each other. Again, the concept of inverse square law, right? Remember that we also discussed this law in Newton's law of gravitation, right? Clear? Any confusion?
No.
Okay, so inverse square law means that according to the formula, we can write this like the formula: G is inversely proportional to the R. Capital G, M are the constant values. So let's suppose if you want to increase the value of G, so you need to decrease your value of R. Okay, this is the concept, that if we want to decrease the value of R, so your value of G will automatically increase because both are inversely proportional to each other. Okay,
Okay.
any confusion?
No.
Okay, and one more thing that is related to the graphical representation, because sometimes they also ask you about the graphical representation, or to just talk about or just to extract the values from the graphical representation. So let's see how graphical representation will be for the variation on the Earth surface and away from the Earth surface. So let's suppose initially when your value is constant on the Earth, so there will be a straight line. Okay, you know that from the origin, we just draw a straight line. So let's suppose till this point we consider that the value of G is constant and the parameters on X and Y axis. On X axis we are having the radius, and on Y axis we are having the value of G, because actually the value of G depends upon the value of R. Okay, and let's suppose if we consider the values of R, so your value of R will be like this will be R, and if we double the distance, so that will be 2R, and then 3R, then 4R, right? And same goes for the value of G. Let's suppose this is the value of 9, or we can say that this value is the actual value of G, that is 9.81, right? And you know that if you are increasing the distance, right, so at certain distance your value will be constant, right, just like in the atmosphere in which we are living. So at certain level the value of G remains constant, okay. But after that you can see on x-axis when you start moving towards right hand side, so actually you are moving away from the earth, so your value will start decreasing, right, exponentially decay, because there is a square 1 over r square. So it means that it is inverse square law, and when we are using a square in the equation, so it means there will be a curve in the graph, so that will be exponential decay. So your final formation of the graph will be like this. Okay, so it will be like exponential decay, and you can see that the initial value is constant till r, and then at 2 it is different. So let's suppose if you compare the value of r, so that is at earth's surface or at the actual radius of earth, value of G will be equals to the actual value of G, that is 9.81. And if we talk about the 2r, so what do you think that what will be the value of G at 2r? Because now you have the formula and you have the concept that how to change the things. So what will be the value of G at 2r?
Um, we will we will do time times divide by 4.
Yes. So you know that G is inversely to 1 over r square. So if you take 2r, to 2 means 2 to the 4. So it means your gravitational value will be decreased by 4 times, right? Just like if we continue this equation, so your equation will be 1 over 2r square, right? It will be equals to 1 over 4 times the value of r, the actual value of r square, right? So it means that your value of G will be decreased by 4 times, right? So that is the
Yes.
value of the 2r on y-axis, right? So now you got the concept. If we are having 3r, so that will be 9, G over 9. Your gravitational value will be decreased by 9 times, because there is a concept of 3 and a square of 3, 3 3s are 9. Okay.
Okay.
So green line shows you that G is directly proportional to R, because straight line always shows directly relation. So G is directly to the value of R. And if we talk about the purple line, so purple line shows you inverse proportion, right? So inverse proportion, because we know that both are in inverse relation, value is decreasing, radius is increasing. So this is the concept, right?
Yes.
Any confusion?
No.
Okay. Okay, let's suppose if we consider one question, because we are talking about the planet, now we are having a concept and this is related to the earth. But let's suppose in your exam, if they will ask about some other planet and just give you all the data related to that planet. So let's see how we have to solve that concept, right? So let's suppose if we consider a question, and question will be like this, that we are taking example of moon, right? So if we take the example of the moon, so the example of the moon basically shows you that the values on the earth is different from the value of the moon, right? Normally it will be less than the earth. So initially, if we talk about the values that is given in the question, so we can say that your density of the moon, so your density will be, so basically your density will be 3 over 5 times of the density of the earth, right? It means if you know the original value of the density of earth, so you need to just convert into 3 over 5 times of the density of the earth. Clear?
Yes.
And the next is the value of g. So the value of g on the moon will be, so I'm writing in a small gm, if your gravitational field strength is 1 over 6 times on the moon as compared to the earth. It means we need to divide 9.81 by 6. So we will get the value of g on the moon. Okay. Now the question is, they are asking that you need to determine the ratio of the moon's radius, that is Rm, and the earth radius, Re. So now we need to find out the ratio of their radius, right? So basically we know that if we start from the first hint that they mention in the question related to the density, so we know that the density on the moon, let's suppose this is our step number 1. So the density of the moon will be equal to 3 over 5 times density of the earth, right? And if we talk about the value of g, so your value of g is 1 over 6 times value of G on the earth, right?
Yes.
And you know that for the density, we need to know about one more thing. If you know about the basic formula of density, so the formula of density is mass over volume, right?
Yes.
Just think from the basics, so you will get the concept easily. Otherwise, it will be difficult that why we are using this value in this concept. So let's suppose if we talk about the volume, so basically we consider Earth and Moon both as the sphere, right? So do you remember the formula for the volume of a sphere? The very journal formula?
Uh, for volume?
Yes. If we want to write the volume sphere that we mostly write in geometry section also, V is equals to 4 over 3 pi r cube. Remember that?
Yes.
So basically, we are going to use that formula because we are using sphere bodies. So your volume of a sphere will be 4 over 3 pi r cube, right? So now we are having three different equations because I already told you that we need to solve the density concept. So we need to know about the value of V. because for the mass we know that mass is not a big deal, but for density, density actually changes your equation, because the formula or the concept for the density is different from the other concept, right? Because for mass we know that there is a law of gravitation, but for density there is nothing that we discussed till now. So now what we need to do, if we take the reference of the density, so that will be step number 3. So your step number 3 will be density is equals to mass upon volume, and we know that your mass will be equals to density times V, right? Now you can see that your mass is automatically converted into density times the volume. Then the fourth step is the value of small g. Okay. So basically value of g will be, right? We know this formula because if initially we start with the concept of density, then value of g. We solve the value of density. We know a mass will be equals to density time volume, because we know that density is this time, because we are only going to find out the ratio, right? We are not going to find out the actual value. We just need to find out the ratio, that how much the density will be less as compared to the earth, right? And now if we convert this value, so what will be your value? Because we know that we are having a mass, and we can replace that quantity with the above equation. So your equation or the step number 4 will be g is equals to g density times v over r square, right?
Yes.
And what we need to do now, we need to do that we need to plug in the value of volume that we already find in equation number 3. So from equation number 3 we can just plug in that value. So your equation will be g is equals to g time density into 4 over 3 pi r cube, right? 3r square. So you can see that r cube over r square, so they will cancel out each other, only r in the numerator will be left out. So your final equation, right? Like this. Clear?
Yes.
Now we know that we need to find out the ratio of their radius. So what we need to do, we need to do like this. G on the moon divided by value of g, because we calculated the equation, right? We just need to write m and e with the equation, so you will get the final value. Okay. So actually what we need to do, we need to write divided by, I'm not writing in numerator denominator because that will make a little bit messy, because we have numerator denominator in both equation. So I'm writing in a separate. So the first one is for the moon, because first we need to write the ratio of the moon, and this is radius of the moon. And second we need to write for the earth. Okay, clear?
Okay.
And you know that what will happen, that this 3 will cancel each other, 4 will cancel each other. Only those quantities which are different, like the density of moon and the radius of moon is separate from the density of earth and the radius of earth, right? Otherwise g, 4, pi, 3, all quantities are constant, they will cancel out each other. So finally what we will get, we will get equation like this: gravitational moon gravitation on earth will be equals to density of moon multiplied by radius of the moon divided by density of the earth into radius of the earth, right? Clear?
Yes.
And now we need to shift the values because we know that we need to find the ratio between Rm and Re. So we just cross multiply the thing. So your answer will be, you know that we need to cross multiply the equation. So you will get G multiply by, right? And this value will cross multiply over here. So you will get automatically on right hand side, you will get radius of moon divided by radius of earth, right?
Yes.
And now you can easily substitute the value. Why? Because initially we started with the concept of density and the concept of gravitational field strength, right? Now we can easily substitute the values and you will get the answer because we know the value of Gm and density of M, right? We only need to place the value. So you will get Rm over Re is equals to your value of Gm or density of the moon. We need to replace that one. So in numerator, the value of Gm will be equals to 1 over 6 time divided by, any confusion?
No.
Okay, now simply you can see that this will cancel out this value and this will cancel out this one, right? Because they are in a straight numerator and denominator, both are dividing each other. Finally, we got only numbers, right? And you know we need to flip the value 1 over 6 multiplied by 5 over 3, right? Because we are having a numerator and denominator. So Rm over Re will be equals to 1 over 6 multiplied by 5 over 3. So it means 5 over 18. And finally, your radius of moon is actually 0.28 times of the radius of earth, right? If they ask about that the radius, so you may drive this equation, or you can also say that their ratio will be equals to 0.28. Clear? And you know that there will
Okay.
be no SI unit. Okay.
Okay.
So in this way, they sometimes ask you the question to drive the question. Sometime like there will be no value, but still there is a important question because you can see that we just started from the basic, right? We know that we didn't talk about the volume and the density concept in the chapter, but those are now very basic concept, right? Because we studied in IGCSE and O levels. So now we don't need to know about each and everything, and we don't need to study about each and everything in very much detail. So that's why you already know about the things. Okay. Any
Okay.
confusion?
No.